We'll go ahead. Thank you for coming. We're gonna see more people coming in a couple of minutes. We know that they were saying that they're gonna be a little bit late. It's a pleasure to have with us today Darian Landolt. Hopefully I pronounced close to. Today he's gonna be representing Case H. It's a large company, so I hope that we have a chance to understand basically all the different technologies that he's working on. He's kind of the manager for the agronomic design and research operations from Case, and based on some of the slides that I have seen, I think that we're gonna be learning a lot about the company and some of the new techs that they're coming soon. So thank you for coming.
Thank you, Ignacio. Thank you, everybody, for joining us today. Thank you for having me. So as Ignacio said, I'm going to talk today, and this will become apparent to you very quickly, but this actually was a title from a presentation I gave at the National No-Till Conference 24 years ago in January. So what I wanted to do when I was asked to come and present, I thought about it, and I said, you know, it'd be really nice to go back and actually look and see what I presented, where we were in precision agriculture and what our mindset was in precision agriculture. So I will start with that. I guess a little bit about me. I've worked in precision agriculture since 1997. I changed careers in 1997 to go into agriculture. I am actually a certified arborist by training, and it's kind of a circuitous way to get to precision agriculture, but I've always been a learner, and my best friend from grad school called me when I was killing trees instead of promoting healthy tree growth and everything. And he goes, we need to do some precision agriculture technology development for our 90 crop consultants. And he said, are you interested in coming and joining Case and working on this? And I said, yeah, I think so. I'm not going to tell you what I'm actually classically trained in. You'll figure it out as the presentation goes on. At the end, I'm going to ask you guys what you think I actually am classically trained in. So anyhow, this presentation, I took slides from the 2001. That's the first half. You'll be able to tell because I didn't change their formatting and everything. I did make them a little better. And I apologize. There's a lot of words on the ones from 24 years ago. I'm normally a very less wordy slide person now. I'm more of a picture person, so I can tell the story instead of trying to read it. So bear with me on the ones that have a lot of words. So anyhow, today, the first part, I'll talk about what I actually do in my day job now, and the format of the group that I work in and how we interact in CNH. Then I'll go start talking about precision ag in 2001. And I also apologize if there's something that I say that seems like it came from 2023. I can't undo what I know, okay? I apologize, I can't undo, and I didn't have the notes on the slides that I thought I did, and that was gonna be my crutch, was I was gonna go back and see what I said actually about each slide. Then lastly, I'm going to pull a handful of examples from the current Case IH portfolio. And the reason Ignacio said that I'm representing Case IH today, and I apologize, is that I'm just not as familiar with our New Holland brand, because in the group that I work out of, most of the products I work with are actually Case IH products. And the technology is dual branded for both of the examples I'm going to use later. All right. So agronomic design and research at CNH is actually under our soil and crop modeling group. And I'm a small but mighty team. We have all of the crop production agronomy areas covered. So we have an application agronomist, a planter agronomist, a seeder agronomist, a tillage agronomist. And then I have hay and forage. Right now they're vacant, unfortunately. And I also have a harvesting agronomy position, and that covers all of our harvesting equipment from the specialty crops. So we have grapes, and we have grape harvesters, and then we have, of course, cotton picking and that. So I cover all of that area in the portfolio. And so really, here's kind of how we work. So we take our understanding of the agronomic needs of the equipment and of the grower, and then we make sure that our voice is heard at the very front end of the actual product development cycle. So instead of building it and they will come, we tell them what they need to build. So we give them, for a planter, for instance, what the depth control needs to be, what the spacing control needs to be, and then anything that's agronomically valid with regards to it. It gets put into the product definition early, and then the acceptable failures and successes get put into it too. So we have reasonable expectations on when we're doing the design work. So we work closely with soil and crop modeling, and we also work very closely with the R&D teams. So we really are trying to drive towards crop cycle optimization for both forage and cash crops. So what do we do for our external customers? We do a lot of field research. So the small but mighty team right now there's 5 of us, and we have 23 projects scattered over 2 provinces in Canada, 6 states for sprayer work, 3 states for planter work. We do tillage research in multiple states, and we have cover crop research in multiple states. So we're just about everywhere with regards that we can. We're where we feel we need to be driving the understanding the most for market share and for our weaknesses. That's how we determine where we go with equipment. So we listen to our customers when we're working with them. So if it's on the front end of a product or if it's in the middle pre-launch, we're listening to what they're saying and we're bringing that back to engineering and to marketing. So of course, having to be the agronomist, we have to be the eyes and ears of the company. So we have to stay current. So we're very active with universities and journals and everything. So we stay 5 to 8 years. I hope you guys are 5 to 8 years ahead of industry and the messaging with regards to the biology for crop production. So we stay in tune with what you guys are working on so that we can bring that into the product development cycle before it's a Me Too product, so to speak. So internally, our customers are actually here, the listing there. So our stakeholders are everybody. So we have R&D, and that includes innovation and product development. And then underneath that is innovation. We have all of the major buckets. Product development, we have both engineering and product validation. We have to teach the product validation people how to collect agronomic data too, so that we have multiple hands. And then our commercial side, we provide information back to the brands on their portfolios so that they understand the product. And so 9 times out of 10, the material that we do in our research group ends up in our marketing material. And so it's very important. And so we follow all the standard protocols that you guys do. I hope our work would be publishable if we could actually take it to 3 years to do the research. We're usually in a 1 to 2 year cycle on things, but we do have some long-term research. So one of the things that's with the current team that we have, we kind of are trying to integrate in. We're looking as we start to progress towards, I would like to believe it's regenerative ag, but honestly it's sustainable intensification. And so my team really focuses on trying to bring systems approach. And this is our real philosophy here. We look at our true mission is climate smart agronomic design is what we want. So we're looking at how do our products work on enhancing carbon input and reducing carbon losses in all of our portfolios. So now on to this. This, like I said, January 11, 2001, perspective on the role of precision ag tech in agricultural production systems. Okay, so today I'm going to talk about sustainable ag a little bit. I thought that was still relevant. And then I'll talk about precision farming a little bit, where it was at that point in time. And like I said, if I wander into modern, just bear with me and forgive me, and just understand that it's really hard for me to not know what I know. All right, so one of the big things when we started talking about precision ag back in the 90s was we were trying to figure out yield variability. And that's exactly what precision ag is. It's all about managing yield variability at the start of it. So what we did was we looked at causes of yield variation and how easy it is to remedy those causes. So, the one that I always laugh about, and it's up there for a reason, is least likely and the easiest to fix is the planter collar, right? Because at that point in time, plant spacing was the big topic of the day. So we always joked about it. Planter collar is easy to fix and it doesn't really matter on it. And then the hard ones are down there in the lower left corner, which is drainage, weather. Last year, 2 years ago, compaction, soil type, organic matter. So those are the areas that they're past. We can do something about it, but it takes more work up above to actually get to it. So then obviously moving into the middle, and that comes fertility and pest and weed management, and then working with planting populations and stuff. And then you get to the nitty gritty, the stuff that actually, the big issues, normal farming is up there in the middle. But the major issue with yield variability in this time period was actually the machines, because the machines weren't capable of doing what we needed them to do, and they were variable. Hydraulic drives weren't the mainstay on planters at the time, so it was ground driven. So if you went from hard ground to soft ground in sand versus a loam, you would change the drive rates on it. So you ended up with variations in planting. We didn't have control of the downforce at that time. So now I'm jumped ahead. Okay. We were dreaming at that time. We had airbags and we had springs. So those are mechanical things. So they were in the process, but the mechanical problems with the equipment was the biggest, what we felt was the easiest to change, and it was the most likely cause of yield variability. So back in the day, we said for sustainable agriculture, we want to increase food and fiber production, and we want to protect the environment. And this is really to preserve the ability for future generations to actually grow food. And I don't think it changed. And the technology and precision farming are the key to making the sustainable solution. So that's kind of our impetus. When we were back in the day, we were always looking, and we were a lot more heavy IPM related too in that time period. It was soil quality and IPM, right? The 4 R's were just rolling out, and then so 4 R's and the soil quality were the buzzwords with regards to it. Now it's soil health, and we don't talk about the 4 R's as much as we should any longer, but they're still there in everything we do. So, all right, I apologize for the lots of words, but anyhow, it's precision farming, as we looked at it back then, was really about production technologies that apply inputs and they actually record the outputs. So as applied files and prescriptions are kind of how this would fall in. And then the technologies themselves would improve the efficiency and the effectiveness of putting the product out and controlling it and collecting the data on the back end. So the prescription as applied and making sure the machines are actually applying the right rate where you think they are at the right time. So, all right. So the key to implementing it is responding and managing to the ecological variation. So obviously precision farming, this is what we thought at the time. It was going to increase the sophistication of the farm sector, which it did. And in doing so, it demanded at that time high-end consultants and higher skilled labor to actually operate the equipment on the front end and on the back end of it. So while we're looking at it, we're increasing the productivity and decreasing the environmental impacts. So we reduce or we target products. And this stuff is actually coming online right now, much more so than it did back then. We reduce, overlap control by a parallel light, a swathing bar back then. I don't know. How many of you in here know what a swath bar looks like? Probably. How many of you are actually in crop production agronomy? Okay, so swathing bar, I'll talk about it later, but most of you had started in 2003 or 2004, probably have never seen a parallel, a swathing bar. But the other way, so we reduced overlap. So that was one of the first things we did in precision agriculture, was being able to stop. We used to use, on a sprayer, we used foam on the wings, a droplet of foam going across, and that's very inefficient because you have to watch outside. You drive like this the whole time and look at that foam. So the other one for increasing the environment is maybe targeting the inputs to decrease the impact. So knowing exactly, so these are all coming online in 2025 very well now, and it's controlling the tips, controlling accurate application, so spot spraying, and site-specific matches application need, which is the stuff you guys are working on in the labs here and working on advancing. But the most important part about precision ag, though, was actually creating a knowledge base. And that knowledge base it's really to replace Grandpa and his father, great-grandpa, their knowledge of the 40 or 80 acres that they grew up on. At this time period, we'd already gone through the first mass exodus of farmers, and farms got big, and they were getting bigger, and a lot of landlords actually weren't farming the land. So the farmer was farming land that wasn't his, and he's moving farther away, so his soils and the behavior here is much different than the behavior over there. So we were losing the cardinal knowledge on the field. So that's where the real value of the precision ag movement was coming from. So management zones, they're critical to precision agriculture because it's the area of the field that responds to a process that is significantly different from any other area in that field. So the only reason you would change the management is because you're going to get a response that's different from that one area to another. So my friend Tom Dorge created this back in the 90s when we were starting to work on stuff together. But he created these different categories on how to characterize a site. And so we got quantitative and stable. That's basically the soil in situ that you have, and you don't get it doesn't change easily. You can change pH, it's on here because we can add lime or add sulfur and drop the pH. But the rest of them, we just can't change easily. They're pretty static in nature. Then we got the dynamic piece in the quantitative. We got weed density and distribution, soil moisture, nitrogen, and then example of that is capturing with the yield monitor was the best tool we had in this time period. Then the qualitative and stable, those go back to the soil properties as they are, but it's actually describing them. So, because like you can tell when you dig a pit, you can tell if it's a hydric soil or if it's not a hydric soil. And then the last piece is what I talked about before, this grower knowledge piece. That's the one thing that we completely lacked when we, but prior to precision ag, when we bought farms. So zones may be classified using relatively low cost surrogates, i.e. topography and bare soil imaging, and then basically the USDA soil survey data sets. All right. At this point in time, in this early 2000s, late 90s, we basically had this for our toolbox. And we still basically have this for our toolbox. It's just expanded in all categories. But our GPS was an RTK, a readily available RTK signal. It was differential. And prior to the government turning off selective availability, you could go out in the field and you could be 150 feet away from the point that you really were. The day selective availability turned off, that all of a sudden you became within meters. So originally GPS was terrible for us. Yield monitors, they've been on combines a long time. In fact, digress. The gentleman that hired me to do this, they were one of the original. Then a new historic marker went up for their yield monitor they invented back in the late 80s, early 90s. So yield monitors have been around, but most people weren't using the data on the combines. Geophysical tools, I'm showing the Verus 3100 here, and Verus took the concept of electrical conductivity from basically the lab to the field, and they built the 3100, which is a six Coulter system. And in all honesty, I own the very first Verus that was ever built. So I had the pleasure of running it for a long time, trying to figure out what it was doing and what it wasn't doing. Then classical imagery, we've been using remote sensed images since we've been taking photos. We started with color infrared, looking at camouflage during World War II, if you remember the Bismarck story. And then we started collecting satellite data in the late 60s with the thematic mapper, but it was at a much larger scale and the pixels were much larger. And then we've been using weather data from imagery for a very long time too. GIS, it was land information systems prior, done by paper. I don't know how many of you, my first GIS class, we had to do it all on paper before we got to go into the ARC lab and start doing it. So we had all the layers and we completely did it. So we had everything had to be indexed so we could do our whole drop down on it. But that was land information. So we've had geographic information systems with ARC being the leader in that. since the late 80s, early 90s. And then obviously application systems. At this time, PWMs were just coming online for sprayers. So the spray tip technology was pretty primitive at this point, and the distribution. So, all right, I'm going to give you a little primer on soils. Are any of you soil scientists? You, all right, so you know this, right? So anyhow, so one of the things back in this time period, and this is when we still had, if we were transitioning from this MCS up here versus going over to AFS services, we were teaching our crop consultants how soils are formed. So basically it's chlorp, and that's, you know, that's 150-year-old concept that was published finally by Jans Jenny in the late 30s. But this is how we look at soil. So it's climate, the organisms, relief or topography, and the parent material over time is how soil is formed. So this is very important to us for what we were driving when it came back to management zones and managing farms. So this slide took me a while to figure out, but really what this is, there's a bunch of journal articles that aren't associated with this anymore, but these were the lead paragraphs, or part of the paragraph, or part of the article, to try to emphasize how important landscape is to agriculture and for management zones. So, all right, so what did we do? So at MCS, or case AFS services, we started out, literally we partnered with Trimble. They set us up with 4400s, and we had all the information. We did everything with RTK. So I don't know, how many of you have ever done RTK surveying? You know how hard it is to keep the radios, right? You probably, did you use 900 hertz or 450 hertz? 900. So you can, that's spread spectrum, that's free, you can do that. These radios that we were using are the 450, and if you're on the wrong channel, you're broadcasting into the ambulances and the firehouses by you. So it's a problem not knowing. Or if the farmer has a radio and he's in that frequency and you walk by his shed and you hear this, and he's like, I don't understand what's going on. And you're like, I hate to tell you, you're actually picking up the broadcast from my radio out in your field. But anyhow, so we topographed thousands of acres with the RTK system, but the problem was we had distance problems. 900s only go roughly a mile, and back then they were about a mile and a half clear sight antennas. With the 450s, we could go a couple miles away, but it was problematic. We set up on HARN sites, so high area accuracy, real surveying network. So we knew where all the geodetic control was in North America. We would go to it, we'd set up on those survey controls. So our fields were actually truly surveyed and at the RTK centimeter level. We evolved, we moved on to post-processing, so you kind of see an evolution. And actually, if you look closely, this is one of the first parallel swathing units ever built by Trimble. I was fortunate enough to be an alpha tester for Trimble when that came out. So what we were thinking with the relief mapping was all of the things we could do to build zones for people. And one of the things that came to light early was the fact that with this survey grade accuracy, we could lay field tile very well with the technology. So we hired an engineer from Texas A&M to join our team, and we started actually putting in precision field tile in the field. So what we did, we took our map, and then we would lay different grids out. So what we would end up doing was we would use 3, 4, 6-inch field tile to do better drainage than to waste the money on the big tile. And then we could change the spacing between the tile depending on the field system. And we worked with, oh boy, at University of Illinois, he studied nitrates in tile water. So we worked on projects with him to do the work and everything. So that was one utilization of the topographic map. So as I mentioned, worked with Trimble on the parallel swathing option. And this is one of the first tools in precision ag that actually showed extreme value, and that the adoption rate was almost instantaneous in the co-ops in the application world, because this was the foam dropout here, and then this guidance bar. It could follow when it first came out, the first passes were only parallel to each other in a linear fashion, a true A-B line. And within a year, you could follow curves for the A-B line. So once it mapped it. So, but the efficiency of the sprayer, the accuracy increased, not much because the foam guys are pretty good. But the thing is, where they gained it was the 20% speed increases that you could do without it. And plus, it decreased operator fatigue from not turning their head, and they focused on their application. So back to my management zones. All right. So now I got it there. So each management zone may actually be different for a different change for different processes. So i.e. seeding rate versus tillage versus herbicide application. Those things may be different depending on how you want to approach it. So the topographic map may work for one area and then couple it with another data layer to get the output that you're looking for. So now, I alluded earlier, now the prescriptions. Now we move from capturing all the field data to moving into writing the prescriptions. And so basically we still have to understand the relevant soil properties. So if I'm using an EM system or an EC system, it's helping me with soil texture and organic matter, and it can, from there, it can pick up CEC fairly well. So those are soil properties. You just have to understand how the proximal sensor, what it's detecting and why it's detecting to be able to write it. And then from there, we write seeding prescriptions off of it, and we can write tillage prescriptions off of the topo map and pieces like that. So then how the process to be performed affects those soil properties. So for instance, for tillage, I'll talk about it a little later when we get to the soil command piece. We know that the government has HEL requirements. You can't do any tillage, but that's not necessarily true. You can do a certain amount of tillage as long as you have a certain amount of residue left. So knowing the topographic map where the HEL boundary is, you can change the tool on the fly by a prescription based off the topographic map. So here's one of our first passes using topography and seeding. So in this case, it was a soybean field, and we seeded with low and high population soybean based on low landscape position versus high landscape positions. And then we used cone penetrometer, lots of cone penetrometer data, but that we utilized, we had a certain PSI cutoff, and then that was the depth that we were going to run our tillage shank at in that time period. All right, next area that we dabbled in back in the day was multi-variety planting. We were fortunate, since we were an equipment manufacturer, we had one engineer who thought it was a great idea to take and split an old cyclo drive into two and then control it separately so we could actually have a switch that we could throw the left drum or the right drum. And so we were trying to figure out how would we approach multi-variety planting. And so the first one we did, which is the easiest one, is hybrid by soil type. So hybrid by soil type, and this just shows some of the economics of two different hybrids based on three different soil types. And that was the low-hanging fruit. We still had to map in the field and turn the switch on, which 9 times out of 10 was me riding on the back of a planter after I flagged the field, throwing my left hand or right hand up to get it to work. So from there, from the simple soil survey, we wanted to start diving in and utilizing more of our data. So the tools that we had at hand were penetrometer. We had obviously standard soil testing, big grids, little grids, however you wanted to look. But most importantly, we looked at more proximal sensing work, and we started writing prescriptions based off of the soil information system predecessor that is floating around out there now. When they were all grad students at the University of Wisconsin, they came and they mapped fields for us. So we used EM data combined with organic matter, thickness of the A horizon. You pick a variable that you can collect with cone penetrometer, EM, and standard soil sampling, and we utilized it to figure out for corn hybrid work. The last one that we did before we lost access to this machine was this. This is actually an as-applied soybean field. And what we did here was we grid sampled for cyst nematode. And then we took the cyst nematode population map where the thresholds were, and we broke it up into experimental plots. And then those were all flagged, and those are where I threw my hand up and down to do it. So we went through it. Actually, on this study, I'm going off of memory, but we used Peking for the susceptible or the resistant variety or high variety, and we used it, and then we had a racehorse, and there was 6 bushel difference between where we chose to put this the Peking and cyst infested areas. And if we used it, we lost those 6 bushel because it didn't have the yield potential as the racehorse. So where we had good soil and didn't have nematodes, the racehorse took off. So it was and then where we had the racehorse and the nematode infested, it got hammered by it. So it was really, actually, this was probably one of the best examples of why a multi-variety planter would be helpful. The next thing we worked on was alternate nitrogen strategies. And this is going to sound funny when I put this word up there because I laughed when I was putting the slides together. But it's really about split season nitrogen applications. Back in the 90s, they were just coming online with the idea of side dress. Historically, you know, I live in Illinois, and we had, you know, I think our rule of thumb, because a certain professor over there, we put 180 units of nitrogen on below Route 70, we put it on between 70 and 80, and above 80, we put it on 180. Basically, put 180 units on, and most of it was fall applied anhydrous in that time period in northern Illinois. We were barely putting spring applied nitrogen out there. So we started looking at split season because we bought Tyler at that point, and this is the first red version of that Tyler sprayer. Became a patriot for us too. But anyhow, we were interested in it, so we did one of many studies with nitrogen and timing. But what we showed was by splitting the season and doing the side dress, we were picking up a huge amount of net return versus putting it all out or putting it out all out late. So we were losing yield when we put most of it out late, and if we put none out, obviously we weren't getting much return at all for that. So that was one area. The last area we were interested in, we had a sabbatical professor who was an economist, but he was strangely interested in compaction. And he's had this love affair with compaction, and we're on tape, I shouldn't have said that. But anyhow, for the last 30 years, he has done something in agriculture and compaction, and he is a geographic economist. I mean, so it's crazy, but the thing is experimental design is phenomenal. So anyhow, he came to us and said, I am interested in understanding tire traffic control in farm fields. So we hooked him up with our main cooperator, and we picked 3 fields, and he put GPS on every piece of equipment that entered the field from fall to fall. And when he did it, you can see this is the tire tracks and of everything going through. So he's got all the different pieces of equipment up there. You got the sprayers, you got the 16-row planter, you got a 9380 on trips. He's got a quad track in the field, the ag chem floater, and then the combine, and then the grain carts. So with it, the first thing is that through the spring season, he only had 30% of the rows that were clear on both sides. So, and there were no rows that by the fall that were clear on both sides. So just think of that. This field had tracks in one season on every row through the field. It's bad, just so you know, that's bad, right? But more importantly, if you look at the 3 or more on one side, almost 50% of the rows in the season had 3 or more tire tracks go through it on the field. Okay, so if you're not a compaction person, the real compaction, 90% of the compaction comes from the first pass. So the first 10,000 pound per axle machine that goes through has destroyed 90% of the deep structure of the soil. But what this is getting to is it's the shallower and trying to undo the shallow, and what I would qualify as compression as much as anything else. So in his one part of the study, what he did look at was what he ended up, he did have a huge decrease in actual stand based on the number of tires that were adjacent to it. So that was the one thing he took away. And I couldn't find the yield data from the study for some reason. I don't have 1999, 2000 yield data floating around anymore. But anyhow, I couldn't find it, but he did have a huge, he had pictures, historically he had the pictures of all the ears and everything, and I couldn't find those because those tell the story better than anything. So that's kind of what we did at the farm. One of the things we moved on and we would talk about, and Bruce knows Steve Favor and Dave Larson very well, so we would have these mental sessions, and we'd always talk about this opportunity because, you know, how's that window look for going out and farming? Because you've got an opportunity cost. If it's rained yesterday, what happens if you start now versus waiting 2 days? But you look at the forecast, you know, this really ties back into a few things that we'll talk about later. It ties into bigger machines, because this was a time period where we were starting to move into wider planters, wider field cultivators, wider tillage. And then we would talk about speed to pick up the efficiencies. And what is the penalty for this waiting? So one of the things from this slide going forward is that we've had an advantage because some of the technology and the genetics have offset some of these penalties. Some of the hybrids and varieties in the past were a little more sensitive to the time, and they couldn't make up for time, and they were much more sensitive to the extreme environmental conditions that they're not so sensitive to any longer. All right, so we talked back then about what is integrated system of smart iron, you know, tools that we need to profitably plan, execute, measure the whole process. So that's when we started working back in the late 90s. We started working we had multiple industry partners, and one of them was Pioneer at the time. And we were leveraging their understanding of their genetics. So historically, you couldn't get the G part of the G by E when it came to hybrids. And so they would provide that, and they were also working on DSAT models to predict on their new hybrids how they were going to do. So they asked us, and a part of our participation was actually to work on tillage. So we were looking at trying to figure out how we could integrate a DSAT component into it. So, you know, obviously maximum yield, but we were looking for our functional criteria in our product development to build an optimum tillage tool. From this case, to build the desirable seed bed for planting, but a tillage tool in general, optimization. So we went through, you know, this is a lot of things going on here to drive down to the crop response. But really what we did was we created a model that would take the initial soil condition by each part of each tillage tool that we had and what the outcome of the tillage process was. And it would generate a piece to plug into the DSAT model so that you could figure out what the impact of soil temperature, soil moisture, particle or aggregate size for the seed to soil contact. So all the things that where DSAT picks up after germination, we were creating the front end of the model so that we could actually populate it so DSAT didn't have the perfect condition, it had the real condition to it. All right, I'm going to switch from the fun things that we did. I'm going to go back to precision farming a little, and hopefully I may just think. So anyhow, the gist here is we need the precision farming to make it easier for to meet the needs and the capabilities of the farmer. And we need to figure out the sequential dependencies in order to make precision farming more attractive to the farmers and more successfully implemented. So, you know, it's not about creating an engineering solution, and it's not about creating a profitable model for marketing. It's actually about meeting the needs and capabilities of the farmer. And I think sometimes that's actually lost on people because some people want a new shiny object. It may not actually increase the ROI. And I don't believe that that's the purpose of precision farming. I think it needs to work on filling the need of a farmer and working on their ROI or working on a labor piece for them. So, all right, I'm going to skip. So back when I presented this in 2001, I threw this up just asked the people how many were participating in these functions, right? And the lion's share of them were already doing GPS grid sampling. They were doing variable rate because they were offered by their co-op and their consultants. Very few were actually using the GIS to actually help with their management decisions, except the very high-end ones. Very few were doing planning prescriptions or seeding prescriptions. Most of them that had bought a combine in the last 5 years had a yield monitor on it because they were standard by that in 2001. But very few had even heard of the information. The Veris was, and it'd been in the market for 4 years by now, so a lot of people had heard of it and seen data from it, and they knew about aerial imaging. Penetrometer, every farmer had a tiling probe, and that's what they equate a tiling probe with, is the Dickie John penetrometer. It's basically a tiling probe. And so that's the extent of their adoption at that point in 2001. So at this point in 2001, I kind of predicted a little, trying to look into the ball and say what was going to happen. And vision guidance on the cultivator, I'm still waiting because nobody has a cultivator anymore. So it makes it hard to develop technology for something that it comes and goes from tillage portfolios. Grain quality sensors, it was hot and now it's not, but it's coming back. So that at that point in time, I figured they would be standard issue. Our combines that we used in the field had NIR technology on them, and we could separate grain based on protein and high oil and fat. Yield monitors, obviously, for more crops. At that point in time, it was just row crops. We had cotton yield monitor hadn't been invented yet. Obviously, wireless data links, high precision GPS wasn't that long after that we started putting auto steer. It was aftermarket, and then we were starting to put it into the tractors very close to this time period. And then once that happened, we started having the control of the machine. So the true auto steer, we didn't need to have the light bar any longer to watch. So it wasn't as much fun, but anyhow, the tractor controlled it. Automated end row turning, obviously it came about 4 years later, 5 years, 4 years. And then the swathing I talked about. And then synchronized machine operation didn't come for another 12 years, 13 years. And then obviously individual spray nozzle control, and we're well beyond that now with regards to it. But those were the things we predicted. The little guy here, this was our crop dog. So this was our first autonomous soil sampling machine. We were working with an engineer that wasn't working on our autonomous tractor program, but that was built in 1998, and it successfully went across to where from point A to point B, and it stopped where it needed to. We just didn't have a soil probe on it, so that was it, proof of concept. But that little ATV had thousands of dollars worth of hardware built inside of it to make it go by itself. So now fast forwarding to what we thought at that time was where we needed to go so that we could get information, because we understood the value of the information, how critical it was for precision farming to be successful. So we figured all these different nodes and everything, but we pointed out the fact that the information from the machines needed to be going to a central location, and then decisions being able to pump. So a two-way street of information. So fast forward, now I'm going to move into 2025. So the Case IH brand is, we have our field ops location, and that's basically that 1999 drawing over here in the high-tech world. The machines are all connected to the cloud, and they're moving information to and from the machines. Like I said, agronomic data is collected at the time of the machine operation. It can be broadcast to the grower's iPhone or to their tablet, and they can also pump back the prescription. So we're starting to see more of a one-stop shop in the field ops setting. So we're starting to see some of the other software packages not necessary. So we're trying to make it easier for the farmer to farm. So he can take his topo map, and he can generate his tillage prescription, and he can pump the tillage prescription right from field ops out to the tillage tractor to go implement. And then it'll collect its as applied file and pop it back, and he can look at the machine data so he can tell how much fuel he's using, if the operator needs to change speeds and optimize. And the same thing goes for the fact that the dealer now, we have access. So we know when the machine needs a new oil filter. We know if it's a leased machine, if he's running it too long. And I know the right to repair conversation that's going on, but this speeds up. It helps most growers maintain things without having to look back at their little notebook in their shirt pocket that they might have lost. So the next thing I wanted to talk about is some of the automation that we've done. I'm going to skip around our portfolio because obviously it's pretty advanced with regards to where precision ag is. I could talk for 2 days probably. But one of the first things that we did was we put our Harvest Command, which is our automation on our combine system. So what it does is it takes just 7 different machine settings, and it's all got sensors on it. So you can change the components inside of that combine to function however you want. So it can be either performance driven, so maximizing grain savings and grain quality, or grain quality, it can focus on the best quality grain so you have the least amount of mog in it, or you can move down to fixed throughput or maximum throughput. But it's your choice when you get in that combine. So what it does is it drives down the need for the expert user, because we're starting to run low on expert users any longer. And so what this does is it takes the expert user and puts it in a button form for the operator or the owner sitting at the other end watching the combines go through the field. So then this information goes back out to field ops. And then you can look and get calculations on how your machines are performing. So you can look at, one of the big ones is how much throughput or how many bushels you get per gallon of fuel. So you optimize. And that's the one thing that Harvest Command and our customers are talking about, is the fact that they're now getting more throughput per gallon of diesel fuel by utilizing it in the system. So with the purchase of Raven, we got a few products, and since we're talking about harvest, the card automation feature component that we got from them. It's really actually pretty nice, because with bigger corn heads and guys driving tractors that may not be professional tractor drivers trying to get grain from the combine, it makes it a lot easier. The 2 machines are talking to each other. They're getting lined up. It knows what the throughput's going to be coming out of the combine, and it's got the ability to move back and forth. So basically, all of the processes that you need a good operator for in the combine and a good operator pulling along to remove the grain are taken care of. So there's a huge advantage for the farming operation. So soil tillage, soil management, this big thing just goes through what a normal farming season looks like. And this is our portfolio on what machines go where. I just wanted to highlight it. And then this goes through all of our soil management properties, but the key one is this piece here. This talks about what the soil command piece is, and that's our automation for it. So those are the machines that have soil command capabilities on them, and they can control different components of it. So soil command, really it's about coordinated control of our tillage settings. So, and then it gives you as applied maps, gives feedback to the owner of the farm right away on the performance of that machine. So the 2 big ones that I like to talk about are the 875. 875 is our disc ripper. It has 5 different settings on it, and they're all meaningful. And if they're not set in the right sequence for the type of tillage you're doing, you can have negative output on it. So what soil command does for it is basically Barney one button. Boom, you hit it, you know what you want. It'll set everything, because 9 times out of 10, when you switch fields, the guy who's switching fields took the time to get on his cell phone to call home to say he's hungry. And at the same time he's getting out, he forgets to set one thing, right? And all of a sudden now he's in ground that needed to have 50% residue coverage. And instead he switches those discs, and now he's bearing 35% or going 35%. He's in trouble with the government. So that feature is a good feature on that. And the 255 is our field cultivator. And what it does, it's sensed to the shanks. So the shank pulls back. So the shank, you want the sweep running flat so that you create a smooth floor that you're going to plant into. Because if the floor is uneven, modern planters are designed to pick up unevenness, and they will adjust their downforce to the unevenness that they're created to try to offset either the gauge wheel contact or the row unit bounce. Well, if the sweeps pull back on a field cultivator, you'll create a rumble strip. And if the planter finds that rumble strip, it'll be sensitive, even though it's 2 inches below the actual soil surface, it will adapt to it. So the planter might hunt, you may end up with an uneven stand due to seed bounce or row unit bounce or bad spacing. So some of I'm going to skip the prescriptions it'll do, but you can do residue coverage that you want. You can do here a variable depth shank on the disc ripper, and you can see down there is the actual fuel, the productivity and the savings, and then over here is actually the field cultivator sweep. And I apologize, I'm not talking fast enough, and you think I would be. Our last product that I wanted to talk about was our Sense Apply technology, and this is a product that we got in the Raven and another purchase. And basically, it's a hood-mounted multispectral camera system, and what it does is it's basically using some NDVI and NR near red edge detection, and it's combining all of them to create. There we go. It creates maps. So it's looking at the vegetation out in front. So this is actually what it's seeing for this 30 to 35 to 40 feet in front of the machine, and it's picking up a whole pass there, and those are weeds that it's identified. So if you were doing see and spray, you would activate the nozzles on at that point in time. But the thing, it picks up biomass. So there's a whole slew of things that the camera is being used for, and some of the technologies that you're used to. So right now we have a nitrogen, fungicide, plant growth regulator, harvest aid, and then we switch over to burn down, and then we have the spot spraying on green on brown technology for it. So, and these are just shows the different crops that we can utilize it in. And if everybody's used to nitrogen, and Ignacio is working on a project from his former employer, he's helping us with the data from this system. But basically, it's doing what we used to do with Crop Scan or Crop Circle and Green Seeker and everything. So it's allowing us to do application based off of chlorophyll content and stress in the plants. All right, so I'm down. I'm not going to give you much time here. So I covered the past, the present, and now the future a little bit. But you know, what I didn't talk about is autonomy, and the reason I didn't is it's just not fully launched in anybody's portfolio yet. It definitely is the future, and you know, the argument between big and small is probably the future, because we're going to see probably larger machines and we're going to see a bunch of smaller machines, and it's really going to be which is better suited for the field conditions and the application of it. But I'm excited, to be honest. You know, the future for me is really about sustainable intensification for agriculture, and all of the technologies that I talked about today are definitely headed in the right direction with reducing inputs and also helping offset the labor shortage that we're going to have. So thank you. And if I got a couple minutes for questions.